In the last lecture, we talked about the two main types of dark reactions, which are the second half or sugar making part of photosynthesis, and we referred to them as the C3 and C4 types of photosynthesis, or we call them C3 plants that use C3 and C4 plants that use C4. At the end of that discussion, I pointed out that C4 plants basically have C3 photosynthesis with some additional steps. And so if we look at the numbers of ATP and NADPH that are needed for each of these processes to fix one molecule of CO2 or put it on its way towards becoming a sugar molecule, we'll see that there's a pretty big difference here, or a significant difference. And so let's summarize this in that C3 plants need 3 ATPs, if we total them up, and 2 NADPHs, okay, from the light reactions to fix 1 CO2. Now the C4 plants, if you recall, have C3 photosynthesis in its entirety plus the C4 cycle, and so that amounts to an additional 2 ATP required. So its grand total is going to be 5 ATP plus 2 NADPH from the light reactions to fix 1 carbon dioxide. Okay? So, all things being equal, which one is more efficient at making sugar from CO2? Well, C3 would be more efficient, and if all things are equal and conditions are ideal, then C3 plants are very good at making sugars, and in a sense they're better because they make it more efficiently in terms of ATP costs. But I said before that C3 plants are very successful in a lot of cases, and a great many of C4 plants are grasses. And when they are grown in climates that are well suited to C4 photosynthesis, they can actually become more efficient than C3 plants. And the reason that can happen is because of a problem that is inherent in C3 plants potentially, and it is called photorespiration. Now, we've talked about photosynthesis, and that's making sugar from light. Photorespiration, literally it would mean the burning of sugars in the presence of light, although it's not literally burning sugars. But since respiration consumes oxygen and not CO2 like photosynthesis, that's where the name comes from. And so let's expand on this a little bit. C3 plants only use Rubisco, as you might recall, to fix carbon dioxide. That's the only option that they have, whereas C4 plants have PEP carboxylase, which first fixes the carbon dioxide, turns it into an organic acid, which then gets hand-delivered basically to the Rubisco molecules. Now, Rubisco, as I've said several times before in this class, is named based on what it does. It carboxylates or oxygenates RUBP molecules, and that's where the name comes from. Well, when photosynthesis is working properly, we're just dealing with the carboxylase activity of Rubisco. But this little O here on the end of the name is the trouble with Rubisco potentially, and that means oxygenase. And when Rubisco goes into oxygenase mode, we'll say oxygenase mode, I guess. It's a pretty good term for it. This is when Rubisco starts, instead of reacting with CO2, it reacts with oxygen. All right. This is referred to as photorespiration. Okay, so photorespiration defined is when Rubisco reacts with oxygen instead of CO2. That is photorespiration. Now, if we think back to the C3 cycle, when it's pumping out sugars is when CO2 is being used by Rubisco. Well, when Rubisco is reacting with oxygen instead of CO2, it's not producing sugars. And so when some of the Rubisco goes into this photorespiration, it lowers the efficiency of sugar making. Okay, so photorespiration is when Rubisco once again fixes O2 instead of CO2, and this lowers sugar production. In other words, if we look back up here to our energy totals or requirements here, the cost to fix one CO2 molecule becomes much greater. In other words, the cost to make a sugar molecule is going to be more than the normal amount of ATP and NADPH requirement, because some of it is being wasted by this photorespiration process, which does not make sugars. Well, why would it suddenly shift into oxygenase mode instead of staying in carboxylase mode? Well, it happens when Rubisco runs short on carbon dioxide. And so this happens if, we'll say, CO2 levels get too low in the leaf. And when does this happen? Well, this happens on hot, bright days. Okay, this whole thing here is favored on, or more likely to happen on, bright and hot days. Well, why does it only happen on bright, hot days? Well, if you're a C3 plant and it becomes bright and hot, you've got a problem, and that problem is you start to use a lot of water, because it being hot, water evaporates more readily, and extended periods of time, i.e. the summer months when you get a string of bright and hot days, over time starts to dry out the soil, and it can become very difficult to keep the cells supplied steadily with water. And so let's take a little closer look at what's going on here in a C3 plant. We'll say hot and bright conditions. Okay, what's going on? Well, as it says in your notes, transpiration rates, or TR, go up. Okay, in order to avoid losing all of the water within the plant closes its stomata, okay, to try and conserve water. And this is when the problem happens. Inside of that leaf, here's our upper and lower epidermis, and we've got our vascular bundles here, and we've got our palisades layer. Okay, I'm going to draw the entire thing. I think you get the picture. But we've got these, in a C3 plant, we've got this spongy mesophyll, and as the stoma become closed, there's only so much CO2 inside of this leaf. And so for a while, Rubisco can get plenty of CO2. But after a while, the CO2 levels start to go down. And at the same time, oxygen levels inside of this leaf start to climb. So O2 levels rise while CO2 levels drop. And the O2 levels rise because oxygen is a byproduct of the light reactions, and in these bright conditions, the light reactions are going like gangbusters. They don't slow down whatsoever. And so what happens here is we start to get photorespiration. In other words, Rubisco, again, starts reacting with, make sure I spell this right, starts reacting with O2 instead of CO2 because it runs out of CO2, basically. All right, the CO2 levels don't stay high enough for it to function with it exclusively. And so overall what happens here is sugar production drops dramatically. A good example of a C3 plant would be creeping bentgrass. And creeping bentgrass is what we would call a cool season turf grass, and it is the preferred grass for use on putting greens in the areas of the world where climate lets you get away with growing this plant. And those areas would tend to be more temperate climates, because creeping bentgrass is what we would refer to as a cool season turf, which is a long drawn out way of saying it's a C3 plant. And so creeping bentgrass has this problem in hot, bright conditions, and this is the main reason we don't see it grown in Florida, or very rarely attempted to even grow in Florida, because we have hot, bright conditions in a great amount of the year. Critical point for most creeping bentgrass is around temperatures of about 86 degrees Fahrenheit. And if you've lived in Florida for very long, you know that we have plenty of days where temperatures get well above 86 degrees Fahrenheit. And so the problem isn't that the plant just drops dead all of a sudden, but the problem is that over time, over a prolonged period of temperatures daily getting over 86 degrees, the plant makes less and less and less sugars and basically has to stop growing. And it stops dead in its tracks. It starts to have roots dying back because they're dependent on those sugars from the leaves. And the plant makes it even harder on the plant, therefore, to uptake water. And so you see an overall decline in the health of, let's say, a cool season turf or any C3 plant in these hot, bright conditions, unless it has some sort of other adaptation to deal with the heat, which many plants do, but creeping bentgrass doesn't particularly have any. Now, that's a C3 plant. What about hot, bright conditions and a C4 plant? So in a C4 plant in hot, when it's hot and bright, what makes it so special for a C4 plant? Well, C4 plant doesn't only have rubisco. It has also PEP carboxylase. And PEP carboxylase, as it says in your notes, along with Cran's anatomy, allows a C4 plant to concentrate CO2, concentrates CO2 into the bundle sheath cells, which is where the rubisco is. So, this is an important point here. C4 plants have virtually no photorespiration occurring, and it's due to the C4 cycle and Cran's anatomy. And so they keep right on trucking, so to speak, making sugars. So we can say sugar production does not stop, because rubisco gets a steady stream of CO2 in the form of that organic acid, and all of the rubisco is only found in those bundle sheath cells, and so this makes a C4 plant much more efficient in hot, bright conditions. So, keeping with our turf grass examples here, creeping bentgrass is a cool season turf. What's an example of a C4 plant? Well, sticking with turf, Bermuda grass is a C4 plant. Bermuda grass is known as a warm season turf. And Bermuda grass keeps right on making sugars with very little problems as long as it has a steady supply of water to temperatures up to the neighborhood of 140 degrees or so. It keeps right on making sugars. Now, it can do this and also conserve moisture because it never runs out of CO2. Creeping bentgrass, to conserve moisture, it closes its stomata, but then it's in a real dilemma. The dilemma is that it needs to open its stomata to keep a steady supply of CO2 coming in, but it can't do it because it will lose too much water and wilt and die immediately. And so the creeping bentgrass takes the tactic of photorespiring some and gradually declining and getting weaker and weaker and weaker until it's eventually dead or killed by a disease because it's in such a weak condition, rather than dying in the immediate future by leaving its stoma wide open, which would cause it to wilt and die. And so Bermuda grass doesn't have that problem in hot, bright conditions. C4 plants, however, don't function so great in lower temperatures, and as it says in your notes, in lower temperature situations, C3 plants are much more efficient. And eventually, if temperatures are prolonged and cold, Bermuda grass will actually go dormant to avoid those conditions altogether. Lastly, in this handout, I talk about bent grass decline or creeping bent grass decline. And I want to spend just a minute or two expanding on what I've already said about bent grass. Once again, bent grass starts photorespiring at around 86 degrees or so Fahrenheit, which is a pretty mild day in our weather. And what this means is it starts using more sugars, or CHOs, we can say, than it makes. And so it starts to get weak, and it's basically slowly starving to death. Just like if you burned more calories than you intake on a daily basis, you lose weight. It gets weaker, the roots start to die back, it becomes more prone to wilting, so we see more wilting. And we also see more disease. And overall, this boils down to what we call a condition called creeping bent grass decline, which is something that turf grass managers who manage this stuff in what's called the transition zone of the United States, the southeast basically, is something that they have to deal with every summer. They go into a period where instead of being so worried about how great the grass looks, they just want to keep the grass alive until the fall temperatures drop to where bent grass is in its sweet spot, where it can then make sugars much more efficiently than C4 plants because it takes 2 less ATPs per CO2 to get the job done. So in hot, bright conditions, C4 plants get the nod. In cooler, more moderate conditions, C3 plants are much better than C4 plants at making sugars.